Welcome back to this explainer. We're picking right up from our last exploration where we looked really closely at edge detection and blur. If you remember, we saw exactly how a human mathematically designs those filters by hand to process an image. Well, today we're taking a massive leap forward into how machines actually learn to see entirely on their own.
Okay, let's dive right in. You remember that sliding window trick we used last time, right? We took a tiny grid of numbers, our kernel, and we slid it pixel by pixel across an image to detect patterns. In our previous explainer, every single number inside that kernel was carefully chosen and hand-designed by a human to find specific things, like vertical lines or shadows.
Section 1. The CNN leap.
So, a modern neural network actually performs that exact same sliding window operation, but with one massive evolutionary leap. The absolutely crucial difference between our old human-crafted method and convolutional neural networks, or CNNs, is that literally nobody programs the kernel. There's no human mathematically deciding what numbers go into that sliding window. Instead, the network is going to figure it out for itself by automatically adjusting its own parameters.
But it has to start somewhere, right? Instead of precise human instructions, the values inside a CNN kernel start out as completely random noise. I mean, if you were to look inside a brand new, untrained network, the numbers in this grid would make absolutely no sense. It's just pure chaos. Arbitrary numbers with zero underlying logic or structure. At this stage, it can't detect an edge, a blur, or anything at all. And this is where it gets really cool, because it illustrates exactly how the network learns. It takes that kernel of random noise, slides it over an image, and basically just makes a guess about what it's looking at. Because the kernel is totally random, those first guesses are almost always wrong. But here's the magic. The network checks if its guesses are right or wrong and feeds that feedback directly back into the system in a continuous loop. Every single time it gets a right or wrong guess, it slightly tweaks those kernel weights. The numbers inside the grid start adjusting and shifting, pulling themselves out of that pure initial chaos. It's an automatic mathematical correction. Step by step, guess by guess, the numbers start nudging in a direction that makes the network just a tiny bit more accurate than it was the time before. Eventually, after thousands or maybe even millions of these tiny automated tweaks, those random numbers lock into a perfectly organized kernel entirely on their own. Suddenly, you've got a grid with high activation numbers cleanly separated from low activation numbers. The chaos is totally gone, and it's replaced by a highly specific, functional filter that the network built completely by itself, just from the feedback of its own right and wrong guesses.
Section 2. The Emergence of Hierarchy.
Now that we have these self-adjusting kernels that organize themselves out of random noise, a massive question comes up. What happens when you stack them deeper and deeper into a network? Well, an emergent spatial hierarchy takes shape. When you stack enough of these self-organized layers together, something genuinely fascinating happens. The network doesn't just look for random patterns anymore. It creates a structured, stepped process for vision, moving from incredibly simple features all the way up to highly complex realities.
Think about the very beginning of this process. In the early layers, the network independently learns to detect basic edges. This is incredible because finding edges is the exact thing we had to manually hand-design a kernel for in the last explainer. But here, the network figured out entirely on its own that finding edges is the most logical first step for understanding an image. It literally built its own edge detectors from scratch.
But obviously, an edge isn't a whole object. As the visual data flows to deeper layers of the network, it takes those basic edges from the early layers and seamlessly combines them. Two edges become a corner. A few curved edges become a circle. The deeper layers actually start recognizing distinct geometric shapes.
Go deeper still, passing those shapes into the final layers of the network, and the system combines them to recognize whole, complex objects. A circle and a few lines become a bicycle. A specific arrangement of shapes becomes a human face. By stacking the layers, the network scales its understanding from a single pixelated line all the way up to the reality of the physical world.
This entire phenomenon is the absolute purest definition of emergence. We didn't explicitly program a visual hierarchy into the computer. No human wrote code telling layer 1 to find edges and layer 3 to find faces. It just happened naturally as a consequence of stacking those self-adjusting kernels together.
I really want to pause on this specific quote because it is profoundly important. Nobody programmed any of that. It emerged from data. The complexity of machine vision wasn't meticulously architected by some software engineer. The structure itself was hidden inside the data the whole time, and the neural network simply organized itself to reflect the reality of the images it was given.
When you really think about how random numbers shift and lock into a system capable of recognizing the world, it's practically magic. And that leads us to an exciting opportunity for those of you following along with us here at AI Tech Hub. Because talking about these networks organizing themselves is one thing, but actually witnessing it happen is another entirely.
So I've got to ask you, do you want to see this fascinating process of a convolutional neural network actually being trained live? Do you want to watch the math shift from random chaos into structured vision right in front of your eyes?
If you do, drop a comment saying CNN right now. If we see enough interest, we'll do a live explainer showing this exact emergence as it happens. Because ultimately, the most provocative thought here isn't just that machines can learn to see. It's that the blueprint for vision itself requires no designer at all. Just data, feedback, and the mathematical patience to let understanding emerge from the noise. Thanks so much for joining me on this explainer, and I'll catch you in the next one.